Good morning, student. First and foremost, I would like to thank our esteemed Vice Chancellor, Pandit Ravi Shankar Shukla University, Professor Sachidanand Shukla ji, for establishing this modern lecture capturing facilities in our university. It will definitely enhance the teaching learning methods. I have no words to express my deep sense of gratitude to Professor Balwant Singh Thakur, who is the in charge of this facility, head Department of Mathematics, and his colleague Dr. Dipti Thakur and Dr. Indra Kumar, Assistant Professor of Mathematics, and particularly my student Mr. Abhishek Katendra, for helping me in preparing this, one of the most important concept of M.Sc second semester physical chemistry. Dear student, today I will discuss one of the important concept of statistical thermodynamics, that is, rotational partition function. And in my previous lecture, I have already discussed the fundamental concept of partition function, and I have also derived the translational partition function. And you all are aware of your course content that you have to study all the partition function. So today I will concentrate only on the rotational partition function. At the outset, I must confess that I have prepared this lecture for the second semester students on the basis of some of the very important books of physical chemistry. So you can refer all those books for details, interpretation and other things. Fortunately, all these books are available in our Pandit Sundarlal Sharma library. And basically, you are all aware of the most important book, the Physical Chemistry Molecular Approach by the Macquarie. And for the students, because I always use very simple derivations, so I have used the book of Thermodynamics for Chemists from Samuel Glaston, and also I have taken some of the derivation from the Statistical Thermodynamics, M.Sc Gupta. As you know, when you start any topic, it is my style that I first tell you what is the formula of rotational partition function. And of course, I will derive this whole rotational partition function, but this is the final, and name itself is a definition, because you know that it is related to, when we teach you the translational partition function, that is related to the translational motion. But now we will discuss about the rotational partition function, and you know that rotation of a particular molecule is very important, and it depends upon the various factors. So when you see this very carefully, this formula, final formula of the rotational partition function, there are certain new things. One, there is a terminology that is giving the moment of inertia, one of the new term you have heard. And second, another term you have seen here, sigma, that is symmetry number. Now, why we study, that is very important, because you all know that learning outcome based framework, that why one will study the any type of partition function, and particularly the rotational partition function. So, you can call what are the significance and the importance of the partition function, rotational partition function. Now, one of the most important application of rotational partition function is that with the help of rotational partition function, accurate or exact calculation of various thermodynamic parameters can be calculated. Number two, you know that statistical thermodynamics tell us a bridge between the quantum mechanics, or sometimes it is called the microscopic properties and the macroscopic properties, and spectroscopy is very important concept. So, with the help of this rotational partition function, we can get some information about the prediction and interpretation of spectroscopic structure. So, I can write it spectroscopy and the molecular structure. And of course, you all know that the behavior of or the effect of temperature on the behavior of the molecules, because it is the distribution of molecules, of course with the help of Maxwell-Boltzmann distribution statistics. And as we have seen in that figure, that there is a question of symmetry number and moment of inertia. So, therefore, with the help of rotational partition function, the symmetric consideration can be understood very easily. And last application is that relation between the molecular structure and the macroscopic observable. So, it is always very important thing, whenever we start any topic, the student must know what are the objective of the studies. Now, I am coming to next point. Now, as I have already told you that it is one of the most important concept, rotational partition function, because whole spectroscopy is also based on that rotational energy levels and other things. Second thing is that it will describe the distribution of rotational energy levels in the molecules of the thermal equilibrium. But you must remember, or you must consider, that this rotational partition function is based on some very important point. One is, I will discuss what is moment of inertia, then quantum mechanical energy levels, and the types of the molecule. Please bear in mind, when you study the translational partition function, I had given some example of monoatomic molecules or diatomic molecules or polyatomic molecules. There is no problem for calculation of the translational partition function. But if I consider the rotational partition function, so you have to be very careful before solving the numerical problems of the rotational partition function. I am just giving one or two examples. Suppose I am taking the example of diatomic molecules. Now, in the diatomic molecules, if we are taking about the nitrogen, so that is called the, of course, it is a linear molecule, but similar type of molecules, homoatomic. But again, if I take the carbon monoxide or the calculation of rotational partition function of hydrochloric acid, HCl, so again you see it is a heteroatomic molecule. So, symmetry number may be different. I will explain what is symmetry number. Second, suppose I am taking some molecules like chloroform or the ammonia. So, you see that in some cases, I am giving one example of, here is the liquid water. You see very simple molecules, water. But when I see the, because it rotates in 3 axes, and if I want to know the moment of inertia of one axis is different, second axis is different, in third axis is different. So, in water molecule, if I want to calculate the rotational partition function, formula will be different, because the three different moment of inertia. Whereas, if I am taking the methane CH4, all this partition that moment of inertia will be same. So, depending upon the types of the molecule, we have to calculate the rotational partition function. So, you can divide it whether it is a diatomic molecules or polyatomic molecule or linear or symmetric type of the molecule, and then where all these moment of inertia will be equal, such type of molecule is called the spherical top type of the molecule. Now, although today I am not teaching you the center of symmetry or spectroscopy, nothing. I will concentrate only on this rotational partition function, but in order to understand the rotational partition function, you must know some information about the structure of the molecules and the symmetry number and other things. As I just told you, that if I am talking about the ammonia molecules, and I have taken this example from the book of McCurry. So, you see that 360-degree rotations. So, like that, suppose this is A, this is B, this is C. In second case, so slight orientation, the spatial orientation, number of indistinguishable orientation, which is very important. You have to consider these orientation. So, in that ammonia case, the symmetry number is 3. Whereas, if I take the methane, where 320-degree rotations. So, there are 4 hydrogen atoms. So, there are 12, symmetry number is 12. Whereas, in water also you see there is only 2 symmetry number. Now, I am coming to the derivation. As you know that the general formula for calculation of any partition function is like that. How can I use the, okay, I can write this place also, where is the, how pennies work. Yes. So, just see that the general formula of any type of partition function is equal to summation Gi, which is called statistical weight factor, exponential minus corresponding energy. If I am talking about the rotations, it must be rotational energy Kb and T. Do I make my point clear? This is the simple formula for calculation of any partition function. Now, if I am talking about the translational, so I have to substitute the value of translational energy. If I want to calculate the rotational partition function, I have to substitute the value of translational energy. That's all. And second point, you all know that in my first lecture, second lecture, I have clearly got statistical weight factor, quantum state. Now, so I am dealing with the rotational partition function. So, first thing is that here you must be very careful that when I was talking about the translational partition function, the energy levels are very closely packed. So, in that case, G value of statistical weight factor or degree of generation is 1. But here, see very carefully, the value of G is equal to 2J plus 1. Now, what is J? J is rotational angular momentum rotational quantum number, or angular momentum quantum number you can call it, and that the value of J may be 0, 1, 2, 3. So, if you ask me, sir, why the value of statistical weight factor is equal to 2j plus 1. Yes, that can also be solved with the help of quantum mechanics, and the quantum mechanics you all know that there is a arithmetic sequence. That means the value of j, that is the angular momentum, is maybe minus j minus 1, 0, j minus 1 plus, like that. So for each rotational level of the j, there are 2j plus 1 orientation of the angular momentum vector. So in a nutshell, you can call it simply that the value of g is equal to 2j plus 1. Okay? Now the second part. That means how do we calculate the rotational energy? Again, I have to take the help of quantum mechanics. Bear in mind, I am not teaching today quantum mechanics. I am teaching only the statistical thermodynamics. So therefore, directly I will write the value of rotational energy. But again, because as I told you that it is a rotational thing, so for first case I will use a linear diatomic type of molecules. For non-linear molecules, so for calculation of rotational energy, I will take the example of, and you are all aware of, if you learn the spectroscopy and quantum mechanics, you all know that what is the formula of the rigid rotor. So it is a simple mechanical process by which one can calculate the types of the rotation. So again, I am just writing again, the degeneracy explains the fact that some levels have exactly the same energy, and this depends on the value of angular momentum quantum number. And just take home message is that for rotational partition function, again I am repeating the same thing, that it must be 2j plus 1. That means if I write, suppose this red color is one energy level, E0, E1, E2, E3, 4 rotational energy levels, and I can write j is equal to 0, j is equal to 1, j is equal to 2, j is equal to 3, like that. Now I am coming to most important part, rotational energy using a rigid rotator. Now again, see, very nicely I have depicted this picture with the help of my student, that again bear in mind that here I am showing a diatomic molecules. So please listen carefully, that maybe HCl. So one atom is there, another atom is there, and there is only one center of mass, and it is rotated towards this mass. So this is a simple rigid rotor model, mechanical model, very useful to explain the rotating system, because when we are talking about the rotational partition function, so we must consider the types of the rotations. Now, if you understand this thing, so here we will consider, because there are maybe the mass of the hydrogen is different, mass of this Cl is different. So here we will use a term which is called reduced mass. So you can ask me, sir, what is reduced mass? So in place of calculation of 2 m1 or m2, what I do, we will use the mu. I will explain. That is called the reduced mass. We consider that both the atoms are rotating towards the center of mass, and the distance between this center of mass is r2, and this is suppose r1. So reduced mass is the motion of the center of mass, which behaves like a free particle. Now one question arises, that suppose there is a rotation and some force is acting, and that is called the moment of inertia, which is very important in this calculation of this rotational partition function. That is a one type of resistance of that molecule to change its rotation. So, because there is a change, and that moment of inertia can be calculated by, if I consider the moment of inertia is equal to capital I, that is equal to mu is reduced mass multiplied by this r square, r1 and r2 square. I will come to that point. So, finally, with the help of, again, derivation of rotational energy is not required for the calculation of rotational partition function. But when you will study the quantum mechanics, you have to derive the rotational energy. So, directly you can write the formula of the rotational energy is equal to J, again it is a rotational quantum number, J plus 1, H you all know Planck's constant, 8 pi square, I is the moment of inertia, and moment of inertia is equal to, you know, is mu, the reduced mass, and I is the moment of inertia. So, again I will just use the pen. Suppose 1 upon, you see, like 1 upon mu is equal to 1 upon, if I write MA1 and 1 upon M2, very simple. So, you know LCM it. So, M1, M2, M1 plus M2. So, mu is equal to M1, M2 divided by M1 plus M2. So, what I am getting finally, mu is equal to M1, M2, M1 plus M2. So, now everything is clear that I am getting 2 points. First point is that, again I am writing same thing, summation J is equal to 0, J is equal to infinite, 2J plus 1, you follow my point? The value of statistical weight factor and then exponential minus the value of J plus 1, H square, 8 pi square I and Boltzmann constant and T. That's all. So, that means now I have to, of course, summation or integration, I will come to that point. So, the next part is, again you can remove this thing. So, yes. So, this is the simple thing. Now, I will derive it actually. Again, I am just writing same thing you see here. Yes, you see that summation J is equal to 0, 2J plus 1, or what happens sometimes, you know that energy is equal to E is equal to H nu is equal to C by lambda. So, that if you see different, therefore, I have given you the different textbook, Atkins or Levine or M.Sc Gupta or McCurry. So, but you are all simple students, so therefore, I am using very simple derivation for that system. Now, before going for the derivation, as I told you that there is a slight modification. What is that modification? In denominator part, I have to use one factor or number that is called the symmetry number. And in the introductory part, I have already given you 3 examples, example of water, example of ammonia, example of CH4, example of nitrogen, example of oxygen, example of carbon monoxide. And always there is, when we are talking about the rotation in the different axes, so that is called the indistinguishable orientation. So, in order to overcounting that indistinguishable orientation, we have to use that symmetry number. So, what we will do, we will, when we will write the final equation in denominator part, we will use that symmetry number. So, for example, if I am talking about the nitrogen, suppose it is a linear molecules and homoatomic molecules. So, symmetry number is equal to 2. If I am taking hydrochloric acid like that, HCl molecule, so then the symmetry number may be 1. If I am taking benzene, the symmetry number may be 12. So, like that. And I am taking this formula from the book of thermodynamics for chemists by Glaston. Now, just for the student clarity and novelty, because you are in M.Sc and studying in the university teaching department, so you must, you know that national education policy, we have given emphasis on the research oriented teaching. So, whenever I am talking about the symmetry number or moment of inertia or one important factor, I will talk you that characteristic rotational temperature. So, I have to write some values you must know. Say for example, I am taking HCl and carbon monoxide, the symmetry number is 1. If I am taking nitrogen, oxygen, symmetry number is 2. For ammonia is 3, methane is 12, benzene is 12. It's just like for information that the symmetry number accounts for indistinguishable orientation of the molecules. And I am taking all these values from the book of physical chemistry by Atkins, page number 473. And you will get all those information, the values from different books, Levine and other things. Similarly, now it is very important. Now, in this derivation, when I derive this equation, there is a very important factor that is called characteristic rotational temperature. Because when I substitute the value of rotational energy in our partition function equation, we will get a particular thing like h square 8 pi square I kb. So, that is that some books it is written as theta. So, it is it is called the characteristic rotational temperature. It gives a way to compare the thermal energy as a given temperature. When I conclude my lecture, then you will see what is the importance of this characteristic rotational temperature. And here I am also giving some of the values of characteristic rotational temperature, like H2, it is 85. Yes, it is a, like partition function is a dimensionless quantity, but you know that characteristic rotational temperature unit is K, Kelvin. So, it is 85.35, HCl is 15.02, oxygen is 2.06, nitrogen is 2.86. Why I am showing this? I will tell after finishing the derivation, and the source is the physical chemistry by the Levine book. Now, what is the importance of this characteristic rotational temperature? First is that characteristic rotational temperature tells us, or it is the temperature at which the rotational levels begin to be significantly populated due to thermal energy. Because if you know the different types of energy levels, and in ground state there are large number of molecules are there. When you increase, definitely there is a population of the energy. So, that is called the, when T is greater than that characteristic rotational, many rotational levels are populated. But in the reverse case, only the lowest rotational levels are populated. So, now I will start the derivation. Okay. So, and it is a very simple derivation. So, let me start from here. First, I will write this j is equal to 0, j infinite. We know 2j plus 1 exponential values of h square 8 pi square I. Of course, j plus 1 we can write like j plus 1 and then kbt. Is it clear? That means this part is rotational energy. Now, suppose here in the previous transformation you have seen that I have used a term that is called the characteristic rotational temperature. So, suppose h square is a Planck constant, you know the values, I will not show you the values of the Planck constant, 8 pi square I moment of inertia and kb, this term is suppose theta. Or I can call it suppose b. In some books it is written b, in some books it is just. And we have seen that when this characteristic rotational temperature divided by capital T values is very less as compared to the normal temperature. Therefore, that summation can be replaced by the integration. So, now I am doing the derivation and I am getting these values. Suppose this h square 8 pi square I kb, I consider it is a characteristic rotational temperature, or in some books it is written like b or a, whatever you want, you can write anything. Now, as I told you that if the value of characteristic rotational temperature divided by T is very low, so that summation can be replaced by the integration. So, in place of summation I am using integration. So, 2j plus 1 and exponential j plus 1. Now, suppose I am writing this, of course, this value is equal to, or I can write suppose b divided by t. You follow my point or not? It is very simple. A mathematics student can very easily understand. I have to integrate it. Now, in place of beta by t, there is no problem. You can write rotational divided by t. Absolutely no problem. But here I am taking the b. Now, suppose you all know that this is a very simple integration. If I write E x suppose beta by t dx, and suppose in place of beta by t I have written here k. So, what is the result of this? 1 by t. I will show you that things later on, but just how do I do solve these things? Now, if I suppose this j plus 1 is equal to z, small z, or it is, what is this? This is actually j square plus j is equal to z. So, So, if I take the differential form of this, so what should I get? dz j square 2 j with respect to g. So, what I am getting, dz is equal to 2j plus 1. So, what I can write here? 0 to infinite. In place of 2j plus 1, this is dz. You just follow this thing, exponential ex b by t dx in place of this dz, and here exponential z mine actually and b divided by t. Follow my point or not? Or I can, what I can write in place of this, I can write e minus z beta by t dz. Now just come to that main, Abhishek, come to that point. Yes, you see, because large number of in M.Sc chemistry, there are some biology students, there are some mathematics students. For it is not working. Yes. So again, it is only for the biology student, because what I did. Now you here see x b t tx, and suppose this b by t or characteristic rotational temperature divided by temperature is equal to k. So what I am getting, of course, for k is, it is 1 by k. So in our case, I am taking x in place of x and dx, 2j plus 1, that is equal to dz. So I am getting t by b like that, because the value of k is actually t by b. So now I am coming to my original. Yes. So it is, suppose if I write b by t, so erase some part, I can erase. Some part I can erase. So what I am getting, now I can use some other color, yellow color, let me. So rotational, yellow color is not showing, so I can use this color, no problem. So what I am getting, 1 by k, and this k b by t. So what I will get, t divided by b. And so I have to substitute the value of b from here. So b is equal to h square, so it will be t. Now here actually h square and 8 pi square I kb. So now I can write like that, 8, our main formula, I kb t divided by h square. This is our first formula of rotational partition function for diatomic molecules. And as I told you that symmetry number is important, so in denominator I can write this thing. So let me write one thing here. So finally, rotational partition function for diatomic molecules 8 pi square I moment of inertia Kb Boltzmann constant T divided by H square. So, in order to calculate the rotational partition function, we have to substitute the value of moment of inertia at particular temperature, suppose 300 K, Planck constant as well as the Boltzmann constant and the. Now, I have just told you that these B can be written as I told you, that H square 8 pi square I Kb is nothing but the characteristic rotational temperature. So, these big formula, and again remember, it is a for diatomic linear type of molecules. If there is a non-linear molecules, the formula will be different. I will not derive that equation, but I will just show you. So, what I can write like that? I can write like that. It is because theta is equal to H square 8 pi square Kb. So, it is so that is also one form of rotational partition function. That means, if you know the value of characteristic rotational temperature, you can calculate the rotational partition function. Because whenever you appear in any competitive examination like CSIR, NET or GET, there is some very small question where very small calculation is required. I will show you in last transparency, I will show you some of the examples that how with the help of characteristic rotational temperature one can calculate the rotational partition function. Say for example, if I just ask you that the rotational characteristic temperature of nitrogen is suppose 80 and symmetry number is 2, calculate the rotational characteristic temperature of nitrogen at 300. So, just you have to, no calculator is required, no log table is required, you have to write 300 divided by 2 into 80. So, that is a MCQ type of the question. So, the last part, yes. So, you see, this is my final derivation, as I have already told you, that rotational partition function 8 pi square I kbt, symmetry number and H square, and of course, this is valid where you see that this value is very less than the temperature, and as because the characteristic rotational temperature is equal to H square 8 pi square I kb. So, that can also be written like that, Q rotation is equal to T by 3. Now, for students, because there are two types of the student, now there is a differential learning. Some students are very advanced learner stage. They want to become a scientist or they want to do research. For them, but most of the examination and most of the books, you will get the simple diatomic linear molecules. But yes, for non-linear molecules, the formula will be slightly different. And I am not going to derive all these things because there are three moment of inertia. If I talk about the CH4 and other things, IA, IB and IC. So first case, characteristic rotation temperature for one axis, characteristic rotational temperature for another axis, characteristic rotational temperature of third axis. That means if I just three axis, if I use these things, you see this multiplied by this multiplied by this, so I will get this type of formula. And rotational characteristic under root of pi, symmetry number 8 pi square 8 kt 3 by 2, because for one case, it's second case and third case. And this IA, IB, IC is called the principal moment of inertia. So for complete derivation, those students want to derive for non-linear type of things at high temperature, they can refer these books of physical chemistry by Atkins. Now the concluding part, today I have discussed the rotational partition function, and as I have already told you that three factors are very important. One is moment of inertia, second is the characteristic rotational temperature, and third is the rotational constants, and of course their symmetry number. So I am giving one example. Suppose in your examination, calculation of rotational partition function of hydrogen or oxygen or nitrogen or carbon monoxide at 300 K. So there are three possibilities. One possibility, they will not provide you the characteristic rotational temperature. In that case, you have to substitute the values of all, like Boltzmann constant 1.38 into 10 to the minus 23 joule per degree, Planck constant 6.62 into 10 to the minus 34 joule second, and then moment of inertia basically is just like 1 point into 10 to the minus 47 kilogram meter square second inverse 1. So it is a very big calculation. For university examination are like that. You have to substitute all this value and you will get this value like 1.57. But for competitive examination, they will give only the values of the characteristic rotational temperature, and of course symmetry number is 2. So it will take only 5 minutes, less than 1 minute. 300 divided by 2 into 85.35 is equal to 1.76. Similarly, you can also, if you understand the spectroscopy, there is a term that is called the rotational constant. So you can also calculate the rotational constant, which is also very important. I am not dealing with the rotational constant, but again, sometimes, again, if you see the books of the Atkins or Levine or McCurry, there are so many numerical problems. So for hydrogen, the temperature is suppose 27 degrees centigrade, and they have given the value of rotational constant. Say for example, 60.8 centimeter inverse 1. So again, from, if you see the relationship between the characteristic rotational temperature and rotational constant. So there is a relationship between the rotational constant and the characteristic rotational temperature. So if you get the value of characteristic rotational temperature, you will get, again, value is 1.71. So don't get confused, because there are, in the rotational partition function, there are many formulas. So you have to just understand that what is characteristic rotational temperature, what is rotational constant, and what is moment of inertia. So you can get the final values of rotational partition function. So thank you very much, and this is the fourth part of my series of lecture on the statistical thermodynamics. In next part, I will derive the vibrational partition function and electronic partition function. So thank you very much.